So, good morning campers and welcome to our next lecture on parallel systems. Today it's going to be all about the basics of MPI, our message passing interface that we will be using throughout the rest of the semester. Now, regarding the overview of this lecture, first I'm going to give you a little bit of information on the general concepts about MPI, like its characteristics, what the programming model looks like, what the startup of MPI looks like, and so on, just so we know why we need it, where it's positioned, and so on. And then I'm going to dive into the details for this lecture, mainly about point-to-point communication and collective communication, which are the two main forms of communication. They're like the two major categories. Either you do the one thing or you do the other thing. I'm also going to show a little bit of source code on the slides, and especially at the end of the lecture there will be a short practical example to show you what MPI usage actually looks like in sort of a real-world code. Now, what's our motivation for using MPI? And I like to do this. I try to have a motivation slide or a few motivation slides in all my lectures in the beginning to not only tell you about stuff, but also tell you about why this is important and why we should care about it. So the motivation for using MPI is the classic example that we need to distribute some data. So say, for example, you have a two-dimensional grid that could represent a country for which you want to do the weather prediction. Could be Austria, for example. Might have a different shape then, but still. And how do you get to parallelize this and have multiple computers work on this problem at the same time? Well, you split up the two-dimensional domain in several chunks. You distribute them to, in this case, 4 different computers. There might be some communication in between those. There might not be, depends on your application and your problem. And for each of those sub-problems, you get a sub-solution, so to speak. So you will have 4 partial solutions that in the end somehow need to be combined, and you arrive at the result that tomorrow it's going to be, I don't know, 12 degrees and sunny, for example. Now, this is obviously an oversimplification. I do not expect weather forecasting to really look like that, but still that shows you what the general idea of parallel programs look like. You always try to distribute data and you always try to share the workload, and at the end you most of the time have some form of aggregation to have a final result. You can also have programs that do not have a final aggregation, where each of the computers just produces its own little result chunk, and then you merge them again to a full domain, for example. Then there's no real aggregation into a single value going on. Anyway, now to the message passing interface. I already told you yesterday that it's a library that's used for distributed memory parallelism. You also already know by now what distributed memory parallelism is. And it's, as I said yesterday, it's basically a means for inter-process communication. As such, for communicating in scientific applications over the network, it's the de facto standard for C++ and for Fortran. And it's quite old. So the original version was released in 1994. And there have been updates in 97, in 2012, 2015, and they're currently working, I think, still on the specification for 0, which will be released, I don't know, maybe next year, maybe the year after, I don't know, but sometime in the 2020s. Now, the point of this information is not that I'm gonna ask you in the lecture exam when was version 2.0 released. Obviously, you're not gonna have a question like that in exam. The point of this slide is to show you that this is a very old standard, but it's maintained continuously, and they keep working on it up to today, and it's actively used. So in the larger group of scientific academics and also industry, it's really almost impossible to find large applications that do not depend on MPI in one form or another. And because of that, specification updates are rather slow, because people aim at high stability and at a high technological readiness level, which means they're not going to release anything that seems buggy, or at least they try as hard as possible. And to show and illustrate how difficult it is, on December 6th of 2017, they just voted for having new voting rules, which sort of shows how exact they are about things. Now, it's important to notice that there's a difference between MPI in terms of its specification and possible implementations. So there are several implementations to choose from. I put one of the most important ones and most original ones up there, which is OpenMPI and MPICH. They're both open source. OpenMPI is the merge of multiple previous MPI implementations that sort of try to pool their efforts, and it's the default on many systems. But then there's also the second implementation I put up there, which is the basis for many vendor implementations, such as MPI from Intel, from IBM, Cray, Microsoft, and so on. Not sure Microsoft is maintained any longer. Not sure about that. Anyway, this is the default on many systems also. For example, if you get a system from Cray, which is a large supercomputer manufacturer, they also provide a sort of specialized MPI implementation that performs really well on their systems. And at its core is MPI-CH. The important thing here is you should never confuse implementation versions with specification versions. Now, the MPI versions, specification versions, as I showed you on the previous slide, of 2.0, 3.0, 3.0 and 3.1, for example, but you will also have OpenMPI implementation versions. For example, there's an OpenMPI version 3.1. That has nothing to do with the MPI standard 3.1, because OpenMPI versioning is just a software versioning, and OpenMPI at its version 2.0 was already MPI standard 3.1 compliant. So whenever you see versions of MPI implementations, these first of all, I mean, there might be some developers who actually lock them towards the MPI specification, but most of them do not. So whenever you see an MPI implementation version, especially for OpenMPI, because they're sort of in the same ballpark of numbers, do not confuse them, and always, if you care about that, check what the implementation actually implements, which specification level. The second thing is you should never confuse implementation adherence with specification adherence. Now that means if you start to depend on implementation specific details of libraries, say there's something that's not defined in the MPI library and you're in the MPI standard, in the MPI specification, and the implementation that you're using just is doing things in a certain way and your application depends on it, then your application will break as soon as you move to an MPI implementation that does things differently. And if it's implementation dependent, it's allowed to, because it's not in the standard. So most of the time you will not touch this. Usually programs written for MPI are pretty portable in terms of functionality, not in terms of performance, but we'll get to that in another lecture. And just because you should always still keep in mind, just because your application is running with one MPI implementation, that doesn't mean it's fully compliant with the standard. Just like a C++ program that compiles with GCC doesn't necessarily follow the C++ standard. And if you start to compile with Clang or with AppleClang or with MSVC, then you run into problems and you realize, what I wrote was actually not correct. So what are the main characteristics of MPI? Well, MPI offers specific tools for sending and receiving messages. That's pretty obvious by now. Waiting and synchronization. You can also identify individual processes. So processes actually know who they are and where they belong, sort of. And it offers additional convenience tools, for example, for partitioning and distributing data, for organizing processes in higher level structures. We will have a lecture on that. And also large-scale I/O operations, because doing large-scale I/O is really difficult. Assume you have an application that produces 1 terabyte of data in 5 minutes, and you should write it out as fast as possible. This is a difficult task on a desktop computer, but doing this with maximum performance on a large-scale system is also really not that straightforward. On the other hand, okay, we get all these convenience tools and everything, but there's a lot of user responsibility involved with MPI. Everything in terms of parallelism and communication is explicit, which means if MPI doesn't do it, it's because you didn't write the code for it. Then program correctness is also user responsibility. If your program crashes, then because you made an error in implementation, at least most of the time. Performance optimization is another issue. We are going to talk today a little bit about blocking versus non-blocking communication and synchronous and asynchronous operation. And there is a multitude of options to choose from that sort of all achieve the same goal but have different means of getting there. And depending whether you choose one or the other, you will get higher performance or you will not. And as usual, there is no free food here, which means it always depends on your situation and your use case, which option is the best. However, even with all this responsibility, there are a lot of advantages, which are the main reason why MPI has been the de facto standard for, I don't know, 20 years now. It's available everywhere, so it's really impossible to find a larger supercomputer which does not have some version of MPI compiled. The larger systems will have multiple versions and multiple implementations to choose from. There are several implementations, so it's not just that you're stuck with a single implementation, and if that doesn't work for you, you have to write MPI implementation code yourself. So you can try to switch implementations, for example. And it's extremely portable to many architectures. Why? Well, because it's mainly just a library. So in one of the last lectures this semester, we're going to hear about other programming models that, for example, introduce new languages where you don't write code in C, C++, Fortran or anything like that, but you write code in something called Chapel, for example. It's a completely different programming language, and with that you need tool support. You need a compiler if you introduce a language, you need a debugger, and so on and so on. With a library you don't. If you develop a library and it adheres to the language specification, which is C in this case, you can just use any compiler that is able to compile C, and it just works in terms of functionality. And usually it's also very high performance. Because MPI has been around since 1994, there have been a lot of people tuning it and working on it continuously throughout 10, 15, 20 years. They really know their stuff, and they really try to get the last little bit of performance out of the network, out of memory copy operations, and so on and so on. Now, a small recap. So, in the last lecture, I told you about Flint's taxonomy and how to categorize programs and architectures. And especially multiple instruction, multiple data stuck out because I told you we will be using that. And if you remember, there are two different possibilities. One of them is multiple program, multiple data. So you have two different source codes. You compile them individually to two different binaries. And when you execute them, they just exchange messages if they know each other's IP or whatever means of addressing you use. Nothing too fancy going on here. The second category of MIMD was single program multiple data, or single program multiple data rather. Which just has a single source code. You compile it to a binary, execute it, and then it just behaves differently on two different CPUs. And this is usually the MPI case, so you could also try to write programs with completely different source files that are compiled individually, but that's rarely the case. Normally, you use SPMD, and SPMD also supports sort of emulating MPMD simply by doing something that you see on the right. So you simply query CPU information to know where you're running on, and if your CPU has the ID 0, you run whatever program A should do, and otherwise you run whatever program B should do, for example. Really short, really simple example, and you will find many codes that are structured like that. So parallelism mainly requires two mechanisms for having parallel programs and having them work properly. First of all, you need a mechanism that spawns processes, and then you need a mechanism for sending and receiving messages and exchanging data. So for spawning processes, this is really more going to operating system details and job orchestration, job managers, and so on. There are multiple ways of achieving this, and we won't look at this in too much detail because at least for what I do, there's not too much research going on, and to be honest, I find it a little bit boring. You just start multiple processes and then they're there and they can work. And also, the startup phase shouldn't be too much of a performance impact. If it is, it's really bad. Hopefully your application will spend 99.9% of its time in computation and not startup. So for now, we simply rely on MPI exec to do all the work for us, and we don't care about the rest. We just know that it works. However, regarding sending and receiving messages, there are many different ways of doing that, and we will definitely look at this in more detail and try to see what the trade-offs are and what the advantages and disadvantages are. And you will not only have many ways of achieving the same operation, but there's also a lot of different operations to choose from, a lot of different functionality to choose from, some of which you will see today in the next hour or so. I already touched on this yesterday a little bit. There's a compiler and execution wrapper for MPI. MPI exec we already heard several times. The compiler wrapper I also discussed already, so shouldn't talk too much about this. The important thing here is for OpenMPI or for most other implementations, there's some compiler flag that shows you the compile options that will be provided to the backend compiler, because if it's a compiler wrapper, it needs to set a linker path and include path and so on. And for OpenMPI, it should be ---- show me. And the second important thing is to note that all additional compiler flags that MPI does not know, so the compiler wrapper, will be passed on to the backend. To the backend compiler, which is, for example, GCC, which could be the Intel compiler, PGI compiler, whatever you use. And that means, for example, if you want debugging flags, well, you just call MPI-CC with -G, and -G is not really understood by the compiler wrapper, so it's just forwarded to GCC. It enables debug symbols and so on and so on. So just do your work as usual. And people like to call this a drop-in replacement. So you just replace your compiler call with MPI-CC, and most of the time it sort of works out of the box. Sometimes you have to adjust a little bit. Yeah, and there's MPI exec, and I think I already mentioned yesterday that formerly this has been MPI run, but it was not really standardized, so there were different options and so on. And MPI exec is now a standardized way of starting MPI programs, which is nice because standardization makes things portable. Then I told you we need options for starting programs, we need options for sending and receiving messages. This is the only slide I think I'm gonna show you throughout of the semester regarding how an application starts on a supercomputer. And then that's it, and you can try in the pro seminar and see what happens, but we're not gonna discuss that in more detail. There are 3 steps. We submit our job with SGE, then we start MPI exec, and then we do MPI function calls in our program that is running. So what do these individual steps involve? For the SGE job submission, it allocates resources, which basically means it just blocks nodes, so they cannot be allocated by anybody else, to make sure that you run on them or you run on a specific set of cores that you get exclusively. It sets the environment, which means it sets environment variables that your program might read, that the MPI implementation might read, for example, because there's a lot of communication going on between this job submission system and the MPI execution wrapper through environment variables. The SGI system or SGE system writes environment variables that are then written by MPI exec to know, okay, how many processes are there in total, and so on and so on. And yeah, as the last step, basically the job script just calls MPI exec. Now MPI exec reads all this information, connects to the individual nodes that are involved, for example the nodes on our LCC2 cluster, and spawns processes. And there are several different ways of doing this. There are several protocols in those implementations, how to connect to the nodes, who talks to who first, and who starts the processes first, and so on and so on. As I said, we don't really care about that, we just know it works. There's a little bit of work going on there, but nothing too fancy. And well, once we have parallel processes, we start our MPI function calls, which means we try to identify our ranks. Rank is MPI terminology for a process or a process ID. We exchange messages and we synchronize callers. For example, if we want to make sure that everybody stops at the same time, which can be useful for debugging purposes and alike. So the first 2 steps should be fairly obvious. Now, what do MPI function calls actually look like? What does an MPI program actually look like? Here I have a small hello world. I should say here that whatever source code I put up on the slides, I try to keep it, first of all, as short as possible to make sure it's readable. However, I still try to keep it as correct as possible, which means I really dislike putting pseudocode up there. If I can put C code or C++ code up there, that is just as short and is actually syntactically correct and just works. So most of the time you can copy paste my code of the slides into a source file, maybe fill in some initialization that is missing or something, and then it works. Just be careful when copy pasting with Unicode and quotes and any other special characters that is not simple A to Z, uppercase, lowercase, ASCII or something, because probably copying out of the PDF will get something wrong. Other than that, I try to keep it as real world and as correct as possible. So what do we have here? Well, first of all, we need to include the header file mpi.h because we need to have the declarations of the functions. Then we call mpi init, which gets the argc and the argv, which is the number of arguments and the arguments themselves that you give to the program. We do this to initialize the MPI environment, and it's important that MPI init is the very first call you do before you do anything else with MPI. So your application can do anything between the start of the main and between the MPI init call, as long as it does not involve MPI. Then we declare a size variable, nothing special going on here, and we call MPI comSize, which sets the size variable to the number of ranks there are in our sort of world, in our program. So if I start 4 programs, size will be initialized with 4 after the first MPI comSize rank call. Then we do the same with rank, which does not give us the number of everybody, but actually the ID of everybody. Then we do a simple printf and we call MPI finalize. And again, MPI finalize needs to be the last call you do, after which you are not allowed to call any more MPI functions. And I just realized that I think my program is not correct because there's a return missing, because the main has a return type int and there's no return value, so compilers should complain about that. I should fix that. Anyway, so that's what a simple program looks like. Now, normally I would ask in the room at this point why you think MPI init takes pointers to argc and argv and not just takes the values themselves. I will try to post the question and see if anybody answers in the chat, just for like half a minute. Think about whether there's any special meaning in there. Hint, there is. I'm trying to see if anybody can figure it out. Which goes a little bit into software development practices and writing good code rather than MPI specifics. Alex probably thinks he knows why, because he's typing. Also, in the meantime, while Alex is typing and giving us a really good suggestion probably, and he's on his cell phone, so probably he's not typing that fast. Note that there's a complete lack of communication or synchronization in here. We're not synchronizing, we're not checking, we're not communicating with anybody else. Everybody's just starting up, trying to find out how many people there are total, everybody's trying to figure out what their number is, their own number, and then everybody stops again. There is nothing else going on. And the other thing that I want to mention here is that you should be aware, some of you might have written OpenMP code in the past, for example, if you did OpenMP parallel systems in the bachelor already, which is just last semester, so there shouldn't be too many of you, if at all. But some of you might have done OpenMP codes with the OpenCL lecture with Peter for comparison, for example. With threading, you have shared memory. Here we have multiple processes, and multiple processes means that you have distributed address spaces and you do not have any storage location sharing. That means that the size variable and the rank variable are different for every process that is executing this code, because every process has their own process image because they run on different nodes, for example. But obviously the data that can be modified, so the pages that can be written to in main memory, are completely different because they are different processes. So even though this looks like a single source code and you call com_size only once in the source code, com_size is actually executed a size number of times, and for rank, for example, every process will write their own different value to rank, and you actually have 4 different variables that are running in 4 different processes, not just a single one in a single process. You should be aware. Alex says that most compilers add an implicit return 0 at the end of the main. Good to know. I still find it bad practice, to be honest, and I'm pretty sure compilers should give you a warning about that, don't they? Anyway, I should check with Godbold. So Alex actually didn't answer the question, so the answer to argc and argv is, every time you write a function that takes a pointer to something means the function likely writes to this memory. Whether it's an array or whether it's a single value or something depends on the details, but I could easily tell MPI init how many arguments there are just by providing argc not with a pointer, not with the address, but simply with the value. The fact that we actually give the address to where this value is stored means MPI init is likely modifying this, or at least has the capability of modifying this value. Whether it's doing that or not depends on the implementation. And this is important because you can write MPI programs in such a way that they do not need an execution wrapper, for example, but you still might want to supply MPI specific flags. And by calling MPI init before you parse your user specific arguments, MPI init can remove them from the argument list. And you will not have to worry about ignoring MPI arguments or MPI parameters on the command line that you do not know about, because you will not see them. So that's the main point. And in overall software practices, that just means that whenever you write a library function that modifies a value, you have to take a pointer. If you write a function that you already know right now is not gonna modify this value, and it's gonna be a simple int or a float or a bool or something, then don't take a pointer, because that will confuse people when they see the declaration. Simply take the value itself. And obviously that mostly applies to C, because in C++ we have more capabilities than that. Now, I mostly mentioned all of this information on MPI init and finalize already. So on init, it needs to be called before you call any other MPI function, and it initializes the library, allocates some internal storage, and so on and so on. And MPI finalize must be the last MPI function called by every process, after which you're not allowed to do anything else. And according to the standard, you need to ensure completion of all locally pending communication. So you must not have any pending send or receive that locally did not finish yet, and you call MPI finalize. But most of the time, this is not an issue. Most of the time, these things are well covered. And well, it performs library cleanup by freeing whatever MPI init allocated. Or at least it should. It really depends on the quality of implementation. Just whenever you develop an application yourself, be sure that you actually clean up all the memory that you allocate. If you need to use a malloc, use free. If you need to use new, then do a delete, whatever. Don't just leave data unfreed at the end of the program because you say, hey, my program ends here anyway, so all the memory will be freed anyway, so why should I go through the hassle of manually clearing my my allocated memory, my allocated data? The problem is it makes it really hard to debug, because if you then produce a memory leak or segmentation fault or something, for example in MPI, and you debug your program with Valgrind, which is a really, really useful tool, you need to start to differ between or categorize between errors that you know about and that are okay because you don't free data and you don't free memory, and errors that are not okay because you don't know about. It's much easier for larger programs to simply be exact and know that you free all the memory, and then Valgrind simply needs to say that your program is clean, there are no memory leaks possible, every byte that has been allocated by you has been freed at the end of your program. That makes it really easy to debug. The second reason is you might not write a standalone application, you might write a library at some point. And if it's a library, it's used by somebody else. So the end of your function, say you implement something called finalize or something, this might not be the end of the lifetime of the process where your library is sitting in. So always try to clean up. Regarding cleanup, I might be a little bit messy in my slides, but that's not because I hate doing this, but rather because, well, I have limited space available, and I do not like to put source codes up with a font size of 4 points or something like that. Now, I mentioned ranks several times, and that's the main information of who you're talking to and who you are yourself. In MPI speak, rank is just a different term for a process or process ID, and it's numbered from 0 to n-1, where n is the number of processes. Nothing too special here. You can query the rank with MPI com rank, and you can query the number of ranks with MPI com size. We already saw that in the example now. And important here is to know that almost all MPI semantics are relative to a communicator or a group, which means whenever you do a message exchange, whenever you do a query operation of what your rank are and is and what the size is, what the number of ranks is, all of this is relative to a group of people, and the group is identified by an MPI group or a communicator, which is basically just a means of aggregating ranks into a set of ranks. There's always MPI com world available. That means everyone in your process that you currently started and use with MPI. And you can create new communicators and groups that hold subsets. For example, if you want to talk to everybody, say on the left side, or everybody on the right side, whatever that means in your program. We will do a little bit more details on communicators and groups at a later lecture. I mention this because it's important. If you do not develop an application but actually a library, you should always create your own communicator as one of the very first things that you do. This is important because, say you want to write a library that is doing, take weather prediction again, always the same example, but it just works. And this is a library that should be included in somebody else's program to provide some nice visualization for the data that your library offers. If the visualization program also uses MPI, and both of you use MPI com world as the communicator, then you get problems with mismatching send and receives. You have send-receive operation, for example, in your library, and you might have one in the application going on at the same time, and you could have a send in your application match a receive in the library instead of the receive in the application again. You need to separate these communication patterns. And the best way of doing this is simply to create your own communicator when a library is doing its startup procedure, because then it's internal, only your library knows about this communicator and the application on the outside has no access. And then even if your library is used by somebody who also uses MPI, they will never interfere with each other. That's really important if you want to write portable code that you can reuse in the future. Okay. Now, this was all the information on the MPI basics and characteristics and why it's useful. Now, we're going to go into a little bit more detail on point-to-point communication, and in a few slides, we're going to move to collective communication. Now, point-to-point communication is aptly named because it means single sender, single receiver. The functions for that are simply called MPI send and MPI receive, not too difficult. It's the simplest form of communication available. It's not necessarily the best, but it's quite easy to get your head around when you write the first program that you just send on one side, receive on one side, and you immediately know what's going on. However, there are multiple different types of doing send and receive. There's a synchronous way of sending, there are asynchronous ways of sending, and for both sending and receiving, there's blocking and non-blocking. And I will detail on that in the next few slides. And this is important because people confuse synchronous and blocking all the time, which I understand because it's complicated, but it's important to know the difference. For all the communication functions or primitives that I show you, I will have a figure on the right that shows what should be going on, and in this case it's simple. We have an array of 0 to 7, so 8 elements on the node on the top left, and it's sent to the node on the top right, and surprise, the node gets the entire data. Not too difficult here. So what does this look like in source code? In source code, your program could look like something like this. It's not the exact source code for the previous example, because in this case we're only sending a single integer and not a full array, but other than that it's the same. We do SPMD, simply by querying is my rank 0 or 1. If my rank is 0, then I do an MPI send with the number which contains the actual value that I want to send. The number of elements that I want to send, the type of the element. I will have details on the parameters on the next slide, so you don't need to take notes or anything, obviously. The next parameter is the target where I want to send the data. 42 is a message tag, and MPI convert again. Not so important, more details on the next slide. And on the other rank, we're simply doing an MPI receive, and then we print out the information here. And it's important to know, because we keep talking a little bit about compilers, and also Alex is doing that. Your compiler might complain in situations like these, for example, because MPI receive uses number without number being initialized on the receiver rank, which is not really an issue because receive actually writes to this value. However, if the compiler only sees the header file with the declaration of this function and the definition is hidden, the compiler has no idea that this value might be written to and is not used in an uninitialized way, and the compiler might complain. So most of the time it's just useful to initialize your data everywhere, even on the systems that you are not using them, because you might be doing something in the future that you don't know about, and debugging undefined behavior because of uninitialized memory locations is usually a pain. There can be cases where this is easier to debug, but in most cases I find it easier to initialize data with some invalid flag that if I ever read this tells me, okay, this data really has never been written to. Because even if I omit this and the data has never been written to, it could just be 0 by accident, and I go like, it's 0 because I never wrote to it and it's initialized, but it's not. And on another system it might behave differently. So try to write clean code as much as possible. Now regarding the parameters, this is what the signature of the function looks like, and at the bottom again you have the full call as we saw on the previous source code example. The first parameter is just void pointer to the source buffer where to send data from, the initial start of the data. Then count just tells MPI how many data elements to send, and data type tells it, oh surprise, which type of data to send. And the type of data is important because it tells MPI about the size of an element, and with the first 3 parameters we basically have half of what a memcopy operation also needs. You need to know where to copy data from, and you need to know the number of bytes, and the number of bytes you can compute by a size of data type multiplying with count. And internally, MPI is not doing two different things or something too different. Just that if you communicate on the same node, MPI might be using a memory copy operation, but if you communicate between nodes, it might just, or it has to communicate over the network. The next parameter is the destination rank. So the target where we want to send the data. Then we have a tag, which is a user-defined message type or category. MPI doesn't really care about those, and I'm not sure if it's implementation defined of how large these tags can be, but I think they're at least something like 32K, so 32,000 or something. Don't use int max or anything like that, but if you stick to anything below, say 10,000 or 30,000 or so, you should never run into issues. These are just used by for differing or differentiating between different types of messages. Say you have a program that can accept push and pull commands, and you want to know if this is a push or this is a pull, just send a message with a tag 0 and a tag 1, for example. Or if you have a more complicated runtime system where you can exchange control commands and you can exchange data, then control commands might use one tag and data might use another tag. This saves you from having to put this in an envelope in your payload that you transmit. The payload can be exactly the data that you want to transmit, and the type of data you can put in the tag. And yeah, at the bottom we see the caller fashion as we already saw it before. Now MPI receive looks very similar. We again have a buffer, but in this case it's a destination buffer where we write data to. We have a count, how many elements actually to receive. There's a typo, it says to send, sorry. There's a data type, which is the type of data to receive, and you might think, okay, this is strange because I have the information already on the sender side. Why do I need this on the receive side? Well, first of all, the receiver might not see the send command in this case, right? There are some other functions where this is the same, where you have a send receive, where both ranks see immediately the same function call, and they just implement the send and receive in the backend. But then again, often you see the count and the data type again as a separate parameter, because MPI allows you to convert the data, which is sort of similar, for example, to a reinterpret cast in C++. So it's possible to send 1000 float numbers on one side, and on the other side simply receive a struct, for example, that contains 1000 floats, which is not the same count and not the same data type, but it's the same size of data, and you can do conversions like that. MPI supports that. Then yeah, we have the source rank, where to receive data from, and we have our tag again, our communicator, and the only additional flag is status, which holds additional information, for example, the rank of the sender or the tag of the message. You don't have to accept this status flag. On the next slide I will show you how to do this, but you might ask, why do I need to query for the rank of the sender? The source rank needs to be already part of the function call signature, right? I have an int parameter source, so why should I query if I already have to put it in there in the first place? And the point is, as shown on the next slide, MPI offers some predefined MPI component constants, which for the second bullet here, wildcards are contained, and you can, for example, do a receive with any source or any tag, which just matches, well, any of them, and then with the status object you can check, okay, I just received a message from anybody, but who actually did I receive it from? And if you want to make sure you only receive it from a specific person, then you wouldn't use any source, but you would rather supply the exact rank ID that you want to receive data from. Other constants are MPI convert, for example, and what I mentioned before, the MPI status ignore. You can use that in place of a status object if you don't really care about who you got this from. And on the top you also see some predefined constants for the data types that can be sent. For example, MPI int, float, double byte, and so on. There are several primitives. There are also user-defined data types, so you can create a so-called derived data type that is a struct or something like that, or a vector, and we will get to that in another lecture, but not today. Now, regarding blocking and non-blocking and synchronous and asynchronous communication, I told you that this is quite difficult to get right, and the most important aspects here to differ between, because they're not the same thing, is when does an MPI function call return, and when does the corresponding message transfer happen? And these are not necessarily directly related. So what is the difference in terms of semantics? The questions that you should ask for whether a function call returned and what that means is, can I overwrite the send buffer? And when is all the data in the receive buffer, for example? Whether you can overwrite the send buffer doesn't necessarily mean anything about whether the message actually left your network card, for example. It's possible the data was copied somewhere else for doing the send operation in the background, and your program continues even though the data wasn't sent yet. And the message transfer aspect is important because the question is whether you need to wait for the receiver to get the entire message, or whether you need to even wait for the receiver to begin receiving the message, maybe not the entire message. Think about MPI as being able to cover everything. You could send a single byte of data, or you could send a gigabyte of data that definitely exceeds the buffer of any network card or anything that is in between you and the receiving node. And this is difficult because there are more components involved than just your two processes that are communicating. I tried to show this with a figure here that has on the left side rank 0, on the right side rank 1, running on node 0 and node 1, for example. So they're separated via some network. And as we move down, we progress in time, and we call a send operation that sends information to rank 1, for example. The question is, how long does this send operation really take? Because your data is likely first copied into some buffer of your network interface card. Then it might be sent over the network, and it might be buffered in some switch. It might be buffered in 10 switches. It might not be buffered at all because these are directly connected. Who knows? Then it might be buffered in the network card of the receiving node where the receiving rank runs, and then it's copied into the main memory, and then the receive operation of rank 1 completed. Now the receive operation needs to wait here, obviously, because if I call a receive and I want to wait for the data to have arrived, I cannot continue this function before the data arrived. That doesn't make sense, right? Because afterwards I will try to use data, although it didn't arrive yet, and there's no point. So this is a waiting time for a blocking receive, but I will get to details on blocking the next slide, that you always have. But on the sender side, how long should you wait? It could be that this just finishes immediately after copying to the network card, or it could be that the operation waits until the entire operation finished across the network. And these are semantics that are quite important and are easy to get wrong. Now let's first talk about the aspects whether you are allowed to use the buffer. There's blocking and non-blocking for that. So blocking, non-blocking always means buffer and never means did something happen over the network already. There's blocking point-to-point communication, which are simply called MPI send and MPI receive. They have no special name because the defaults are blocking. That means once this function returns, you are allowed to use the send or receive buffer. As you see on the source code on the right, after we do a send, you can immediately put new data into the number buffer, for example, because you know for a fact that after the send operation, after the send function call returns, the number buffer will not be used any longer by MPI. You can override it, you can just also leave it as it is. The operation might not have finished yet, so the data might not have been sent yet, but in any case, you can override this buffer again. If the data has not been sent, MPI copied it to an internal buffer, for example. You don't have to care about that, you just know that you can rewrite information into the buffer. And on the receiving side, you know, as soon as MPI receive, the function call finished, whatever data you wanted to receive will be in the buffer and you can just read it from there. Now, what's the difference to non-blocking communication? Non-blocking communication is represented with the MPI functions ISend and IReceive. The I comes from the word immediately because they return almost immediately. They do not wait, they do not block. What happens here is that you tell MPI you want the send operation to take place. However, you promise not to reuse the buffer before calling an MPI wait call and waiting for the wait call to finish. So this is often used for latency hiding and for overlapping communication and computation. Because if you check the latency number slide of my previous lecture last week, there are probably, I don't know by heart, but probably there are some numbers on network communication latencies, and they should be much higher than just doing a computation with a few numbers of float type or something like that, for example. So it's really stupid to do a blocking send or receive operation and wait for the information to arrive. In the meantime, you're blocking. You're probably busy waiting for most MPI implementations, which means you're using the full CPU, checking every possible clock cycle whether information arrived already, and then you continue. And this time is something that's not used. It's just slack time that you waste. So it's much smarter to tell MPI, I want to send information, do it somehow in the backend. In the meantime, I will continue something. Between the I send and the wait, you can do useful computation as long as you do not touch the number buffer. And then at some point when you think you need to reuse the buffer again, there's nothing more meaningful that you can do in the meantime. You issue an MPI wait, and after that you know for a fact that you can reuse the buffer again. And for receive, it's the same. For the receive operation, you tell MPI, I want to receive data, just please do this in the background. In the meantime, I will continue my other work. And once I call MPI wait, I will wait until the data actually really arrived, and then I'm able to reuse buffer. The important thing here is that between the I send and the wait, you're not allowed to access the buffer, and between the I receive and the wait, you're not allowed to access this buffer, because the operation might not have started, might not have finished, might be ongoing, and so on. So that's blocking and non-blocking. The next thing is synchronous and asynchronous send modes. So this is important because synchronous and asynchronous refers to whether the network operation has taken place or when the network operation takes place, and it has nothing to do with blocking and non-blocking. It only exists for the sender side. There is no receive synchronous asynchronous differentiation, because for receive it doesn't make sense. A receive in terms of network operation cannot do anything without receiving data. You can tell MPI, please do a receive operation, and I promise not to access the buffer, as we saw with non-blocking receives. But with synchronous and asynchronous, this doesn't make sense, because you need to get the data anyway. There's no way to say, okay, I'm trying to do an operation without where I want to read data and the data hasn't arrived yet. There are 4 different modes that you can choose from. The first one, or actually I don't want to order them, so it's an unordered list. It's just an information, because it's not like the first one is synchronous send and you should always use that one, but we will get into that. The first one on this list here is synchronous send, S-send, which will wait for a matching receive, which means it will not try to buffer anything on its own. It will not try to do anything special. This call will definitely block your program, not only for you to reuse the buffer again, but it will also block for the receiving side to have called an MPI receive that matches this send call. Which means it needs to be the correct source, it needs to be the correct communicator, and so on. If the receiving side then posted the receive, your send operation starts sending data and the function call can return, not before that. Then there's bsend, which is a buffered send. MPI allows you to allocate buffers specifically. It will not wait for a matching receive, but it will copy the data into an MPI internal buffer that you can allocate. This is useful for some architectures where you have special kind of memory locations that are low latency, fast to access, and so on. But this is rarely used in simpler applications, so to speak. This is more of a performance optimization. Then there's ready send, which is the so-called ready mode. This is a quite dangerous one with a lot of developer responsibility. So this is a very fast operation in the sense that it requires the receiving node to already have posted the receive. It will not wait. It will assume that whenever you call rsend, the receive operation is already waiting for the data. If it's not, your program is malformed, it does not adhere to the MPI specification, and you might get undefined behavior. Now, you might be confused, why are there so many different ways? Why isn't MPI automatically doing the right thing? The problem is that all of these send operations involve different protocols in the backend. For example, if I do a synchronous send and I wait for a matching receive, I need to do sort of a handshake. I need to tell the other network partner that I'm communicating with, I want to talk to you, please tell me once you are ready. This I am ready flag will be sent by the receive operation, and then the send knows, okay, the receive has been posted, I can safely send the data now. This requires a handshake across the network, and the handshake always means latency, because you need to exchange messages. They're very small, they might just carry a single byte of information, but you still need information. Somebody is ready to receive data, I can start sending the data now. The rsend operation doesn't require this handshake because the rsend operation requires you to ensure that the receive has already been posted. You need to ensure this in your program code, however you do that. And this way, it doesn't have to do a handshake. It just can start sending the data because it knows the receiving end is ready for receiving already. Which is a performance optimization. But this is quite difficult because if you do a send with an arbitrary amount of data, the receiving side needs to have a buffer allocated for that. And with an send, with the handshake, for example, in the handshake you could communicate, okay, I want to send you data, can you please get ready for it? And the data will be 128 kilobytes. And then you know, okay, I'm going to get 128 kilobytes. How large is my network buffer? Do I still have room for that? With an rsend, this already needs to have happened because I just start sending the data. If a buffer is too small, then undefined behavior because the receive hasn't posted yet and you're not ready to receive the full data. Now, luckily, the standard also, the MPI specification also mandates a standard mode, which is the normal send that we've seen. And this leaves it up to the MPI implementation to decide which mode is best. It will make sure that your program runs correctly, so it may buffer or it may not buffer, it may wait or not wait for a matching receive. It's up to the implementation, but this is what we use most of the time. Send might, for example, just be used by send for really large data. And for really small data, it might just use a buffered send or a ready mode send or something. You don't have to care about that, you just use it. And using the correct implementation for send is just up to the MPI implementation. So it will decide, depending on, I don't know, the size of the data that you want to send, who you want to communicate with, what the architecture is that you're working on, and so on, which mode to select when you just call MPI send. The problem with all those modes is also that they've grown a little bit in terms of history. Choosing the right one for whatever you want to do is really a trade-off between program complexity, between latency and bandwidth that you get. And there's usually, I mean, you can use send, the normal send, and the MPI implementation is trying to do something that has proven to be a good idea in the past, but it really depends on your use case, on your architecture, on the program, how you communicate, and you might achieve better performance or a better developer experience by using one of the other send modes, but then you trade it off with increasing program complexity or decreasing performance and so on. So this really depends on what you need. Send, however, I can mention is useful for debugging, because the send operation may buffer or may not buffer, and it may or may not wait for a matching receive. It can hide incorrectly formed MPI programs by avoiding deadlocks, for example, because you do a send operation that might block your process, but because you send so little data, it's buffered and the send call returns, and then you don't have a deadlock. So if you want to debug your program and you want to make sure that the send and receive matching of functions is fully correct in your entire program, you could try to replace all your send calls with send calls, because these will definitely wait for a matching receive. And if you have a deadlock because you're calling send and receive in a wrong order on the one rank and on the other rank, send will simply block you and you will see the deadlock that you have. And for small data, send might hide it. For many MPI implementations, the limit has been, for example, I think 64 kilobytes. So below 64 kilobytes, it will buffer. Above 64 kilobytes of data, it will just block. And if you send less than 64, you might not see the deadlock that you actually have in your program, or the possibility for a deadlock. It's 10 minutes past 9. I remember that I did not ask you last week whether you actually want to take a break, because it's a 2 hours lecture and some students like to just continue. Some students like to take a break and get a rest for 10 or 15 minutes. This is the last slide for point-to-point communication. I will continue to explain that. If anybody has any specific recommendations whether we should take a break or not, please just type it into the chat. If nobody speaks up, I will probably just keep going and then we can finish a little bit earlier, which I think makes more sense. But if you want to take a break, I don't mind either way, just let me know. Also, speaking in terms of lecture quality, I saw that some people are doing, especially Rainer Böhme, doing fancy green screen stuff where they show and embed a live video of the person talking, which I'm not doing, obviously, and you're just seeing my hopefully not too boring slides and listening to my oh so beautiful voice. So if you think that seeing me might make this lecture more followable, to put it like that, or more entertaining, whatever, let me know and I will see if I can work something out. Otherwise, we can also just continue like that. I just don't want to keep this too boring. Usually I'm in the lecture room, I try to be a little bit funny and have a self-deprecating sense of humor to sort of have a good lecture communication mode going on and not to bore you too much. But if you think that this can be improved somehow by seeing me or doing anything else, just let me know. Anyway, message order preservation, the last thing for point-to-point. Message order preservation is a really important concept of MPI. It means that messages cannot overtake each other if there are several requirements. The send and receive operations need to have, or the send operations rather, because we're talking about send operations overtaking. You need to use the same communicator, you need to have the same source rank, and you need to have the same destination rank, which just means identify uniquely that you're actually communicating to the same process. If this is the case, then a second send operation will never overtake a first send operation. This is guaranteed by MPI. If you have an implementation that does that, it's doing it wrong. This is regardless of any blocking, any synchronization, whatever. If you post two sends with the same communicator, source, and destination on one side, and you post two receives on the second side, you know for a fact that the second send will never match the first receive or vice versa. It will always be done correctly. Just make sure that communicator, source, and destination are the same, because otherwise you don't know exactly that you're really communicating with the same destination rank. Okay, that's everything so far regarding point-to-point communication. Are there any questions so far? Nobody seems to be speaking up or typing, so I hope I don't have any unanswered questions. Then let's just continue on with collective communication. Collective communication is really useful because by now you've seen that we have point-to-point, but if I want to talk to more people, I need to issue a separate send operation for everybody that I want to send data to. If I want to do a broadcast where I want to give a specific piece of information to everybody and I have 10,000 ranks, well, as you can imagine, that's a bad idea. You need to start to implement some tree-based patterns or something yourself. Well, guess what? MPI actually has functionality for that. Collective communication is basically just for convenience. Everything you do with collectives could also be done with send and receive, but you don't want to have the workload. And they're just available for some frequently used programming patterns like distributing data, gathering data, broadcasting, and so on. Now the difference to point is that they can involve several ranks at the same time, not just two. However, it must be called the collective communication by all ranks in the communicator. So collective communication is always done for a communicator, or basically also a group, but it needs to be done by all of those ranks. If you have a communicator with 8 ranks and you try to do a collective with just 4 of them, you will likely get a deadlock or something else. This is not allowed by the standard. Collective communication must be called in order by the ranks. So even if you have all ranks doing all the communication, you cannot have half of the ranks doing the first communication call first and half of the ranks doing the second communication call first and then do the other way around. If you have one collective communication going on and the second afterwards, the first one must be finished by everybody before the second one can be finished by everybody. There's no interleaving. It's important to differ here between the local and the global finishing of an operation. So the collective communication is locally finished when your local operation has finished, which means a local send or a local receive, whatever happened in order to fulfill this collective. But just because locally your function call returned, for example, because locally everything finished, doesn't mean that everybody finished with this operation. Other ranks might be slower or might be faster than you. Globally, it's only finished when everybody did this collective operation that you wanted to do. And to make things nice and useful, we have those available as blocking and non-blocking variants. Now, I'm not sure if I mentioned it now before with the synchronous and asynchronous operation, that for the synchronous and asynchronous send modes, you also have non-blocking variants for all of them. Not sure, I think I wrote it on the slides, not sure I mentioned it, but that's just to complicate things. So in total, we have something like 8 send modes for whatever performance bit you want to get out of your code. Okay, what do they look like? So the first one I want to present is MPI scatter and scatter V. What it does is just send chunks of data to multiple ranks, including root. You see here our array that we want to send. After the send operation, for example, if we want to send 2 elements of those 8 to everybody, root gets 0 and 1, the second rank gets 2 and 3, and 4 and 5, and 6 and 7, and so on. And root also copies its data to our own receive buffer to make sure that everybody can use the same function signature, which works quite nicely. It's a simple way of partitioning and distributing the data. It's not necessarily the best, depending on what you actually want to do, but it's very straightforward. And there is also a variant called scatter V, which allows you to specify how many elements to send to the individual ranks. So scatter just is a special case of scatter V that assumes you send the same amount of elements to everybody. If you want a more generic case, you use scatter V, where you can specify. For example, send 7 elements to rank 1 and 2 elements to rank 2, and so on. Now, what does the function signature look like? Well, we have a send buffer that we use to send data from. We have a send count and we have a send type. You already know by now what these do. However, now, because the scatter call is collective and called by everybody, so everybody's calling the same function really, also in this function we have the receive buffer, the receive count, and the receive type. And I mentioned before that this might look like duplicated information because the send and receive count should be the same. However, you can change data types in between and sort of do a reinterpret cast this way. Send buffer, send count, and send type are only significant at root, so the remaining ranks that are receiving anything from this scatter operation are not reading those. The receiving data will end up in receive buffer, and as I mentioned before, receive buffer is also used on the root because root is just copying its own chunk of data into the receive buffer starting from the send buffer. So you can have the same source code for everybody, including the root who actually sent this data out, and you don't need to differ that root continues to work on the first part of the send buffer while everybody else needs to work on the receive buffer, which would be an additional SPMD aspect where you do a if rank 0 and if any of the other ranks and so on, which we don't want to have. And the only other thing that's special about this is the second last parameter, which is the root, which is simply the rank of the MPI process that should distribute the data. Everybody else will be doing a receive. Now, to show this in source code, your application could look something like this. We have global data, which is just an integer array of 4 elements. We have local data, which is a single integer. And if we are rank 0, this is also sometimes referred to as the master rank. I'm not sure this is politically correct these days, but anyway, I didn't use this terminology before. So if rank is 0, then we initialize global data with something, which means global data is only initialized on the first rank, on rank 0. And this, for example, could be read from a database, this could be read from a file, this could just be initialized. There might be some reason why you only want to do this on one rank. It could be, for example, that whatever means for initializing data you use cannot be parallelized because it's a random number generator that is inherently serial. And you don't want everybody to do that, just do it on one rank and then distribute the data that you generated. And after that, we do an MPI scatter operation with global data as the send buffer. We send one integer to everybody. The data will be received in local data. Again, we will receive one integer for everybody, and rank 0 is the rank that initialized the data, so it will be the root, and afterwards everybody will have one integer in its local data. Okay. And also important for collectives is that you cannot mix them with point-to-point in the same communication operation. So you cannot try to do a collective call and answer a collective call that sends data with a receiving point-to-point communication on the other end or something. I mean, you can try, it's not going to work. So don't do that, don't try that. Of course, this also works the other way around. So we can, actually Daniel had a question. What happens here if you only have 2 processes? In this case, should receive 2 integers. Well, if you have 2 processes, then If you have two processes, then yeah, you only receive two integers. So the first root, the first process will get one integer, the second process will get one integer, and that's it. And the remaining global data at positions 2 and 3 will not be used. In this case, you could also, in this case, it will just be like a normal send receive operation. So this also works the other way around. We can also receive data, or rather send data to the root from everybody, called gather and gather v. It just works the same way, only the other way around. Again, it's a simple way of collecting data, not necessarily the best, depends on what you do in your program. And again, we have a gather v, a generic variant that allows to vary the counts of elements that you want to send to the roots depending on where you send them from. I'm not gonna show any function signature here. I think I have one in the example at the end of the slides, which we're gonna reach soon, but it should be fairly obvious what's going on here. The last operation that I want to detail on here is MPI broadcast, because it's very simple, it's very useful, and it just sends the same data to everybody. It just sends copies of the data. In our case, our array of elements 0 to 7 will be received by everybody. And everybody can do operation on the entire data. This might be, for example, initialization data of your program that tells you how large the domain is that everybody is working on, or some specific constants that do not change even for different chunks of data that you do computation on. Usually it's something like size information and stuff like that. Now, an important thing here, because I want to talk about performance. Performance is really important. That's why we have MPI. It's been optimized for 20 years, I told you. But that's not the only thing that's important. We do not only care about performance, we also care about productivity and being able to write readable code. Now you might wonder whether doing a broadcast, like you see on top of the source code comment, is the same as doing the operation below, which just says if I'm rank 0, I issue size number of send operations, and on every other rank I do one receive operation that matches each send operation that I do on the rank 0, and this will essentially just be a broadcast. Otherwise, after that, everybody will have broadcasted the broadcasted data. Now you might think that this is just exactly the same, or you might not. You might wonder whether one is better than the other one. Again, this would be a question that I would ask into the room and see what your reactions are, or maybe just point at people to make them feel uncomfortable because they have to answer and they didn't pay attention. I can't do that right now, but I'm just gonna go ahead and answer this. There are two things involved here. One of them is the actual performance. One of them is the readability and the productivity of the readability of the code and the productivity of the programmer. First of all, performance. This could be an implementation of broadcast. So what you see below the source code comment, the doing individual send and receives, could be actually what's happening in MPI internally when you do a broadcast. But then again, it might not. MPI might figure out a smarter way of distributing the data by, for example, building a tree structure or something. MPI only knows, okay, you want to broadcast the data. The user doesn't care at all how this is achieved. Just do this. And usually, I mean, it's not mandated for this function call, but the general mode of operation of MPI is to do everything as fast as possible. So the user can assume that if I do a broadcast, MPI will figure out a smart way of doing this and doing this really, really fast. This saves me the trouble of figuring out how to do this really fast and how to encode this manually. However, this is only one option. We're going to see a slide on that on the next slide, more information on that. But that's only one thing. The other thing is, don't forget about the semantics of the program, writing readable source code and your productivity. Think that you might be writing source code like that for, I don't know, some exercise here, and then you have an exam and you want to study what you wrote in October when you do the exam or when you prepare for the exam in January, and you need to figure out what the hell did I do 3 months ago. Or you work in a company, you wrote a parallel application, and 6 months from now you need to do some bug fixing, and you need to figure out there's a send and there's a receive, and I iterate through the things, and do I miss a rank because if I does not equal rank and so on. You need to figure out later on yourself that this has been a broadcast, or this is supposed to represent a broadcast. which is a lot of work for you. Just write MPI bcast. It's shorter and it's immediately obvious what's going on. This cannot be anything else but a broadcast, because that's what the standard says. That's what the specification says. Also, this saves you from writing comments. I will probably keep saying that in the pro seminar. The best in-source comments are the ones that you do not have to write. If you have a variable that has some cryptic name, and in order to explain to the reader what this variable means, you have to write a comment, you're probably not doing it wrong. Just give the variable an identifier that immediately tells you what it's supposed to be used for. If it's coordinates, for example, in a coordinate system, you can just use x, y, z, because that's universally accepted. If you work on some physics problem and something is just called p, I'm not a physicist. I have no idea what p means. Probably most of you are not physicists either. Just don't give it a single letter identifier. Call it something like pressure, call it temperature, call it something that you immediately know what this is supposed to mean. And the same is here for this. In order to know that this is supposed to be a broadcast, you might implement something like this and put a source code comment on top of it. This is supposed to be a broadcast. Then another employee after you is going to rewrite the source code, because he realized or she realized that you don't need to do a broadcast. Only half of the ranks need this information. So he rewrites the code, or she rewrites the code, but they're too lazy to modify the comment. And then you have a comment that says this is a broadcast, and you have code below that is not doing a broadcast. Something like that cannot happen if you try to use more, say, semantically speaking code, and simply in this case using MPI bcast, because you immediately know what's going on. It's very short, and it's the best option of all of them. Now, all of this in terms of productivity, but as I mentioned before, it's also about performance, and I promised you a slide on that. Here it is. Collective communication patterns have the advantage that they allow MPI to choose automatically. They give MPI the freedom of choosing automatically at runtime what should or not what should happen, but how it should happen. So this can depend on multiple parameters. It can depend on what operation you do, whether it's a broadcast, a scatter, a gather, an all scatter, and so on. I have some other examples later, but only enumerating, not explaining them. It can be the number of the ranks that you have. It can even be the location of ranks. If the MPI runtime system knows where the ranks are located in the network topology, it might try to do things differently. It could depend on the size and structure of data. It could depend on hardware capabilities. So below you see 3 examples. You could have a sequential algorithm for implementing a broadcast, for example, which has the complexity of the number of ranks, because if I have 10 ranks, I need to do 10 send operations. That's just a long code example you saw on the previous slide. A smarter thing, which many MPI implementations will try to do, is, for example, to use a tree-based algorithm. When the first step you send to one rank, then in a second step, you and the first rank that you send data to send simultaneously to somebody else, and then those ranks and everybody start sending in a third step, and so on, which of course has a much lower complexity because you're building a tree structure. You should know that from algorithms and data structures. And third of all, which is something that you might not think of, is that there could be a hardware operation that supports this. You could have a special hardware optimization that allows you to realize a broadcast without having to do it in software. For example, there are broadcast addresses or multicast addresses that are possible with IP communication. Most of the time you're not using something like IP, but you're using something more complex. The underlying structure is usually not Ethernet, but something like InfiniBand and so on if you work on the larger supercomputers. But very often they provide special optimizations in order to do operations efficiently that are frequently occurring in source code. They know that there are some operations that are used by, say, 70% of the researchers. Then they will try to provide hardware optimizations for that. And then the MPI implementation doesn't have to do this in software. It can simply tell the hardware, please do this type of operation. And usually when you have specialized hardware for something, it will never be slower than software. Software will never be as fast. Okay. There's also MPI barrier, which is quite simple. It causes every rank to block and wait until everybody else reach the barrier, and then everybody can continue. Normally barriers are not needed because we have explicit data communication, because we work in distributed memory. I mentioned this several times. Explicit data communication inherently also synchronizes. It's sort of impossible for you to do a receive operation and continue with the assumption that you received data without the data actually being on your node, without actually the data having been transferred across the network. So obviously this also has inherent synchronization. You remember, for some of you that did OpenMP, for example, or pthread programming in operating systems, here you need explicit synchronization because the data communication is implicit. With threads, you can just access global data without having to send messages around, but because here the data communication is implicit, you need to explicitly synchronize. In MPI, because explicit data communication needs to happen, synchronization is inherent or implicit. Just the other way around. And for this reason, normally you don't need an MPI barrier. Often it's useful for debugging or profiling. For example, if you want to make sure everybody waits at this, say, location, and then you try to start a debugger and try to see what their state is and so on, or you use it for profiling if you want to benchmark your I/O operation, for example, if you want to write data to disk very fast and you have some computation going on before that. Computation might finish earlier and later for some ranks, and then they might start to write data earlier or later, and this might screw up your profiling. So you could put a barrier between the computation and the writing of data, so you know everybody writes at the same time, and then you can do profiling knowing that the storage system is stressed at the same time by everybody. Whatever you do with debugging and using MPI barrier, just don't forget, please, to remove it in production or release. This happens extremely frequently, very, very often, that people forget MPI barrier in their codes. And you need to remember, for all of those collective communications, they are really expensive. It makes no sense to do a collective that needs to be involved with everybody. Remember, everybody in a communicator needs to do the collective. This doesn't make sense if you only want to exchange data between a few of those ranks, or if you don't need to exchange data at all. For example, MPI barrier, only used for debugging. You leave it in the code, but it means you need to communicate with everybody because everybody needs to check, okay, are we complete? Can we continue now? And if this is a global communication going on throughout your supercomputer of, say, 100,000 ranks, and this happens at every time step of a loop, for example, at every iteration of a loop that you're doing in your program, this is really, really expensive. So don't use collective communication unless you know that you need it. If you need to talk to everybody, that's fine. If you don't need to talk to everybody, then don't use a collective with everybody. And don't forget barriers in your code if you move to production or if you do a release. A few more operations that are collectives, in this case aggregations. So we have MPI reduce, which allows you to aggregate data. For example, you could do a sum operation and simply summing up all the values. In this case, we have different values, 0, 1, 2, and 3 stored on 4 ranks, and after an MPI reduce with the MPI sum operation, big surprise, the root rank is going to have the number 6 as the result. Important here is that this requires a reduction operation that is associative. So it should not matter whether you do the operation with the result of x0 and x1 and the result of x2 and x3, or you first do x0 and x1, then you do the same operation with the result and with x2, and you do the same operation with that result and x3, which is simply associativity. This is really important. You might have heard about this in the past already in computer science, I'm not sure. I usually discuss it all the time in my parallelism and operating system courses. This obviously holds for integers, because whether I do a plus b plus c or b plus c plus a or whatever, you will always get the same for integers. This is not necessarily true with floating point types, because floating point types in their IEEE 754 implementation that we have on our processors nowadays, they are not designed to be exact in terms of math. They are designed to be, first of all, quite fast, because floating point computation, for those of you who know how floating point numbers are implemented in hardware, you know that this is comparatively complicated. They're designed to be very fast, and they're designed to be reproducible, which means if you do the same order of operations with the same data, you will get exactly the same result. This might sound stupid, but this is not guaranteed for every operation out there in computer science. So this is an important guarantee that if you do the same things in the same order, you will get the same output. However, it does not guarantee associativity. So if you do an MPI sum or product or whatever with floating point numbers and you run this several times, or you run this with a different number of ranks, you might start to get different results. So there's the parameters of MPI reduce, which is nothing too special. Again, we have a send buffer, we have a receive buffer, we have a count, which is the number of elements, And data type, the only important thing here is the op, which is the reduction operation. And there are several predefined ones for MPI. You have MPI max and min, for example, which do exactly what they say or what you think they do. Then there is sum and product. There is logical and or XOR. There is bitwise and or XOR. So you can see that this really resembles most of the operators that arithmetic and logic and bit operators that you have in C already available. And you see that MPI tries to mimic the basic use cases of everybody else. There are two special ones, maxlock and minlock. They give you not only the maximum and minimum of your data, but they also give you the allocation, the rank which held this data. So if I look for the global maximum and I find that the first time I hit this global maximum is rank number 7, then location will be 7. You can also have user-defined operations. However, they must be associative, as I told you before, otherwise the result is not exactly defined. They require a specific function signature. We might have a lecture on that later on. Let's see. And they need to be registered with MPI, so MPI knows about them in the first place. Not too important right now. Just know that what you see on the left side is not what you're stuck with. If you come up with something more fancy that you need, you could also implement reduction operations on your own. Might not be as optimal though, so if you try to re-implement something that MPI already offers, you might not benefit from any specialized optimization or hardware optimization or something like that. So, some additional MPI functions, and afterwards we have a small example and then we're done for today. There's MPI W time, which is a really, really useful tool for profiling. It simply returns you the time in seconds since an arbitrary time in the past. W for wall clock time. I hope most of you know what the wall clock time means. The next lecture, I think already, will be on metrics and a little bit of time measurement. So I will explain what's the important concept here. But some of you might already know what wall clock time means exactly. Anyway, the arbitrary time could be the time you started your process, the time that the machine booted up. It could be midnight, 1st of January 1970. Who cares? You just know that it's the same point of reference for everybody in your program. Then you have MPI send receive. It's just a convenience wrapper for doing a blocking send and receive. Saves you from writing an if and doing that yourself. There's all reduce, all gather, and so on. So if you ever check the MPI function listing, you will find a lot of functions that are prefixed with all. They are just the same as the non-all versions, but the result will be available everywhere. So we saw what a gather operation looks like. We saw what a reduce operation looks like. And if you do an all reduce, you will not have the aggregation value only on root, but afterwards root will, or it's like the semantics of first gathering it to root and then doing a broadcast. But as we know, if MPI knows that this is what you want to do, call an all reduce, and MPI might do something smarter than first gathering at the root and then again doing a broadcast. It might do something intermediate, so you don't have to do the broadcast from root, but people will start to distribute the value. Then we have scan and xscan, which are just inclusive and exclusive prefix reductions. Those of you who did OpenCL know a little bit about this stuff. There is MPI wait, we already saw, which will block until a non-blocking operation has finished and you can reuse the buffer. However, there's also MPI test, which is a non-blocking version of wait. So if you want to do a non-blocking operation, at some point you cannot wait any longer until you need to refill the buffer, you call wait. If at some point you just want to check if it finished, but if it didn't finish, you just continue on with something, you do test. So test never blocks. Test just tells you, did it finish or not, but whether it finished or not, you can continue your work and check again later. There's also MPI probe and MPI iProbe, which allows you to check whether a new message is available without actually receiving it. Because MPI wait and MPI test require a send or receive to have been posted before, and you cannot say, I want to check whether there's a message for me to receive, but I don't want to post the receive operation first. With wait and test, this doesn't work. But probe and iProbe sort of allows you to probe the memory buffer or probe the network buffer, that's why it's called that way, or allows you to inspect the buffer and see, is there a message for me, and if I call or receive now, will I get this message or not? Might be useful in some cases. Now, let's move on to the example. people like to do this with naive matrix multiplication because it's well understood. Most people know what it looks like, and it's a picture book example for different MPI collectives to be used, so why not use it myself, I thought. We have 4 ranks in this case that distribute a matrix to do A times P equals C. For this operation to do, you need to distribute individual rows to individual ranks. In this case, as you see, we want to distribute, just the illustration of the operation, distribute the row 2 to rank number 1. We need to do a broadcast of B because for the matrix multiplication operation, everybody needs every column. And then once we computed C, we can again do a gather operation. And the code looks like what I have on the right. Of course, some includes. We define a size, so we don't have to hard code integer literals throughout the code without knowing what they mean. This is always very useful because you just give your number a name, and that way I know that it's supposed to be a size. If somewhere I have a loop down there later on and I see 4, I don't know, is that a size? Is that the number of ranks? What is that? Then we globally allocate 2-dimensional arrays, and I just have some functions, fill matrix and print matrix. They're not on the slides, so just assume that they are available and will be linked somehow into your program. Then we have variables for the rank ID and the number of processes. We call our init as we have to. We check the number of everybody and the total number of ranks we have available. Then just some little bit of error handling that is usually missing from my slides because of the space. In this case, if the number of processors does not evenly divide or integer divide the size of the matrix, I just fail because it's more complicated to do it that way. You probably know what this means. And we just generate some initial data on root. It could be random data, could be some identity matrix, whatever. After generating the data on root, we compute the boundaries that each rank needs to work on. So while numprocs will be the same for everybody, my rank will be different for everybody. My rank will hold different values. So for every rank, we'll compute different start and end points of the rows of our matrix. And then we do a scatter operation. And here we already use the start because that's the point where we start to fill data in. That's like the receiving buffer. The size of the entire data is the size of our matrix divided by the number of ranks that we have. We use integers in this example, so the data type is just MPI int. We just send the same data type and the same number of elements that we also want to receive. The root process is the one that generated the data, so it needs to be root in our collective communication and so on. And because I said we need a broadcast for B to send matrix B to everyone, well, let's just do an MPI bcast, which is much shorter, obviously. Now that we distributed all the data, we can do the actual computation. So everybody starts at their own starting point and ends at their own ending point, which are different for every rank. And then we just do our normal matrix multiplication. I'm not going to go into details. You should know how this works. If you don't, just read it up on the internet. There's a ton of examples. And after we finished our computation, we just can do an MPI gather, which simply gathers all of our results back to our C buffer. And again, we sort of have the same parameters that we had for the scatter operation. So same sizes, same data types, and so on. After this operation finished, rank 0 will have all the information, all the results of matrix C. We print it, we do a finalize, and then we exit, and that's it. And this with a fairly large font size on 2 slides. I mean, yeah, so 3 slides sort of, including visualization. Just fill matrix and print matrix definitions, and the int main I think is missing. Otherwise, this will compile, or should compile, this will work, and this is a fully parallel program. You might not get the best performance out of it. There are much smarter ways of doing matrix multiplication, probably both in terms of algorithm as well as in terms of MPI implementation, but it works. Okay. Lastly, I only discussed this in the pro seminar, and some of you might not attend this. I think I have a few students that only want to listen to the lecture. How do you submit a program? Assume that we just implemented the program I showed you on the last 3 slides, and we compile it, and we have an application that works. How do we now start this on a cluster? We can use SGE, or we have to use SGE on the LCC2 cluster. And you see an example script on the left where we specify the submission queue. Once again, we want to change into the current directory, otherwise it's going to be the home directory that we work in. We want to set the name of the job that runs. We want to redirect the output stream to this file, otherwise you're going to get automatically named files that hold the job ID. We want to have output and error stream arrive in the same file and not different files. And the most important flag here probably is the parallel environment, which controls how many nodes we get and how many cores per node we get. And remember, this is the total number of cores overall. This is not the number of nodes or anything like that. And then we start our application with 8 ranks, and this is matrix multiplication working. And on the right, I just show for comparison how a script with Slurm looks like, which is very similar. It's a little bit shorter because many things that people have been doing all the time in SGE scripts have been made default in Slurm. For example, changing to the current directory, there's no flag for Slurm because Slurm automatically does this. There's really no point in always starting in your home directory. People don't like that. The same thing happens for output and error stream. I think Slurm automatically joins them, so you have to specify flags if you don't want this behavior. And other than that, the flags are different, but they do the same work. For submitting to a specific partition, which is Slurm speak for queues, you use the -p flag. Job name is -- job name. Output is -o, which is the same actually. And the nice thing about Slurm is you can just use MPI exec here the same way you did it with SGE, but Slurm can be a little bit smarter because if you take a look here, there's actually duplication of information. You need to specify that you want 8 cores total for your parallel environment, and then again you need to specify that you want 8 ranks, which is most of the time going to be exactly the same number, but it's not a single point of information, and not having a single point of information increases the chance for errors and programmer mistakes. At some point you want to modify this to 16, you increase this to 16, but you still are not going to get more than 8 cores. And you get strange performance and something strange happens. Most likely in this case, OpenMPI will even warn you with oversubscription messages, but Slurm has a nice way of getting around this problem by taking a different MPI execution wrapper, not using MPI exec, but srun, for example, which can do the same thing, and srun will just read the information from the parallel environment, and you don't need to specify any additional flag here. And this saves you the trouble of having to specify the same value multiple times in your source code, which in this case is our bash script, and saves you the trouble of debugging for a long time while stuff is not running the way it's supposed to be. But as I said, unfortunately, we have to work with SGE. Just in case you want to work on larger clusters, in case you want to do a master thesis with me or any of my colleagues and do a little bit with MPI or larger supercomputers, we have some at UIBK I mentioned. Also, if we have something really interesting, we can get access to much larger systems. At the moment, I'm doing a project with astrophysics where we run experiments in France at a supercomputer in Paris with 16 or up to 20,000 cores. And we use MPI for that, which is quite nice. So, anyway, to conclude this lecture, actually, Marcus has a question. How do I comment out parts on the top of the script? Double hash. Yes, double hash should work exactly. You don't even need a white space or anything. Just put an additional in front and it should work. Okay, a summary about today's lecture. We discussed the general concepts of MPI, its main characteristics, what the programming model looks like, that it's distributed memory and not shared memory, that it's different process images and data, and you can just access data without communicating, and a very little piece on MPI startup, which is everything we're going to hear in this semester. Then the main 2 categories of communication, which is point-to-point and collective. I gave you examples on why or when you might need them, what the difference in performance and productivity is, and so on. Gave you information on all the collectives that are, or not all the collectives, but several important collectives that are available. There are many more available than what I showed you now, and all of them are available as non-blocking variants also. We discussed a practical example, which is matrix multiplication, which shows how to actually write an MPI program that should sort of work out of the box as I showed you on the slides. This concludes the lecture so far. Are there any questions from your side besides the ones